Hi everyone, this is Hannah and this is my presentation on muscle contraction. The process of muscle contraction and relaxation has four major phases: excitation, excitation-contraction coupling, contraction, and relaxation. Each of the phases are then broken up into several smaller steps. There are 18 steps to muscle contraction and relaxation. The first phase in the muscle contraction relaxation process is excitation. Excitation is comprised of 5 steps. Step 1, arrival of nerve signal. Step 2, acetylcholine release. Step 3, binding of acetylcholine to receptor. Step 4, opening of ligand-regulated ion gate and creation of end plate potential. Step 5, opening of voltage-regulated ion gates and creation of action potentials. The first step is the arrival of the nerve signal. A nerve signal arrives at the synaptic knob and opens the voltage-gated calcium channels. From here, calcium ions enter the synaptic knob. The calcium ions stimulate the synaptic vesicles to release acetylcholine into the synaptic cleft. One action potential causes exocytosis of about 60 vesicles, and each vesicle releases about 10,000 molecules of acetylcholine. Next, the acetylcholine diffuses across the synaptic cleft and binds to receptors on the sarcolemma. These receptors are ligand-gated ion channels. For step 4, 2 acetylcholine molecules must bind to each receptor to open the channel. When it opens, sodium ions flow quickly into the cell and potassium ions flow out. As a result, the sarcolemma reverses polarity. Its voltage quickly jumps from the resting membrane potential of negative 90 millivolts to a peak of 75 millivolts as sodium ions enter, and then falls back to a level close to the resting membrane potential as potassium ions exit. This rapid fluctuation in voltage at the motor end plate is called the end plate potential, or EPP. Areas of sarcolemma next to the end plate have voltage-gated ion channels that open in response to the end plate potential. Some of these are specific for sodium ions and admit them to the cell, while others are specific for potassium ions and allow them to leave. These ion movements create an action potential, which means the muscle fiber is now excited. Now we'll move on to the next phase in the process, which is excitation-contraction coupling. The next 4 steps of the muscle contraction relaxation process are grouped together into a phase called excitation-contraction coupling. Excitation-contraction coupling refers to events that link action potentials on the sarcolemma to activation of the myofilaments, thereby preparing them to contract. Step 6 is action potentials propagated down T tubules. Step 7, calcium released from terminal cisternae. Step 8, binding of calcium to troponin. Step 9, shifting of tropomyosin, exposure of active sites on actin. In step 6, a wave of action potentials spreads from the motor end plate in all directions, like ripples on a pond. When this excitation reaches the T tubules, it continues down them into the cell interior. In step 7, action potentials open voltage-gated ion channels in the T tubules. These are linked to calcium channels in the terminal cisternae of the sarcoplasmic reticulum. Thus, channels in the SR open as well, and calcium diffuses out of the SR down its concentration gradient into the cytosol. In step 8, calcium binds to the troponin of the thin filaments. In step 9, the troponin-tropomyosin complex changes shape and exposes the active sites on the actin filaments. This makes them available for binding to myosin heads, which brings us to the next phase of the muscle contraction relaxation process called contraction. Steps 10 to 13 of the muscle contraction relaxation process are grouped together into a phase called contraction. Contraction is the phase in which the muscle fiber develops tension and may shorten. The mechanism of contraction is called the sliding filament theory. It holds that the myofilaments do not become any shorter during contraction. Rather, the thin filaments slide over the thick ones and pull the Z-discs behind them, causing each sarcomere as a whole to shorten. Step 10. Hydrolysis of ATP to ADP and phosphate, also called P sub I, and activation and cocking of myosin head. Step 11. Formation of myosin-actin crossbridge. Step 12. power stroke, and sliding of thin filament over thick filament. And step 13, binding of new ATP and breaking of cross-bridge. The myosin head must have an ATP molecule bound to it to initiate contraction. In step 10, myosin ATPase, an enzyme in the head, hydrolyzes this ATP into ADP and phosphate. The energy released by this process activates the head, which cocks into an extended high energy position. The head temporarily keeps the ADP and phosphate bound to it. In step 11, the cocked myosin binds to an exposed active site on the thin filament, forming a cross bridge between the myosin and actin. In step 12, myosin releases the ADP and phosphate and flexes into a bent, low-energy position, tugging the thin filament along with it. This is called the power stroke. The head remains bound to actin until it binds to a new ATP. In step 13, the binding of ATP to myosin destabilizes the myosin-actin bond, breaking the cross-bridge. Myosin is now prepared to repeat the whole process. It will hydrolyze the new ATP, recock, also called the recovery stroke, attach to a new active site farther down the thin filament, and produce another power stroke. The final phase of the muscle contraction relaxation process is a phase called relaxation. When the nerve fiber stops stimulating it, a muscle fiber relaxes and returns to its resting length. Step 14. Cessation of nervous stimulation and acetylcholine release. Step 15. Acetylcholine breakdown by acetylcholinesterase. Step 16. Reabsorption of calcium ions by sarcoplasmic reticulum. Step 17. Loss of calcium ions from troponin. Step 18. Return of tropomyosin to position of blocking active sites of actin. In step 14, the nerve signals stop arriving at the neuromuscular junction, so the synaptic knob stops releasing acetylcholine. In step 15, as acetylcholine dissociates from its receptor, acetylcholinesterase breaks it down into fragments that cannot stimulate the muscle. The synaptic knob reabsorbs these fragments for recycling. All of this happens continuously while the muscle is stimulated too, but when nerve signals stop, no more acetylcholine is released to replace that which breaks down. Therefore, stimulation of the muscle fiber by acetylcholine ceases. From excitation through contraction, the sarcoplasmic reticulum simultaneously releases and reabsorbs calcium ions, but when the nerve fiber stops firing and excitation ceases, calcium ion release also ceases and only its reabsorption continues. In the sarcoplasmic reticulum, calcium ions bind to the protein calsequestrin, which allows the SR to store a large amount of calcium ions without them precipitating as calcium salts. In step 17, owing to reabsorption by the SR, the level of free calcium in the cytosol falls dramatically. Now, when the calcium dissociates from the troponin, it is not replaced. In the final step, step 18, tropomyosin moves back into the position where it blocks the active sites of the actin filament. Myosin can no longer bind to actin, and the muscle fiber ceases to produce or maintain tension. This has been my presentation on muscle contraction. Thanks for watching.